Welcome, ladies and gentlemen, to the webinar. Great that you're all here. Today, I would like to give you an introduction into VirtualLab Fusion. And so this will be the first part. So I would like to start directly now with this new graphical user interface, and therefore I simply will switch to the new VirtualLab Fusion. And now you can see there are 5 main graphical user interface components in VirtualLab Fusion. So here in the upper part, we have the ribbons. Here in the center, we have document windows. So for example, here you can see an harmonic field. This describes, for example, here an electromagnetic field of a Gaussian beam in a transversal plane. And then we have here on the right side, we have the property browser. So this is always connected to the document window which we have activated. I will come to that a little bit later. Also, you can switch here from the property browser to the VirtualLab Explorer, and here you can see all windows which are open in this session. And you just can also select them by this VirtualLab Explorer. Here in the lower part, we have the message window. So here, VirtualLab typically will log the simulation time, and it will give you some warnings if you generate some of them. And we also find here the detector results in the left lower corner. So here all the outputs from the detectors will be displayed. So we will see this later. And here in the right lower corner, we see the computer resource monitoring. So we see here how much CPU and how much physical memory is currently required. So please note that, for example, here this black part here is not the memory requirement of VirtualLab, but this is due to the requirements of the operation system, Windows, and the background services. And here's also a very small green part, and this is really the consumption of physical memory of VirtualLab. And if you do some simulations, it might be that this green part will grow. So you always have control about the memory consumption. So let's start with the ribbons. So we have to distinguish between permanent ribbons and document-specific ribbons. So the 5 left ribbons, they are always permanent, so you will always see them, whereas we have document-specific ribbons, which means that if I select here another document, also here different ribbons will be shown, and by this ribbons you can now manipulate, for example, or change the view of certain document. So let's directly go here, for example, to this harmonic field document, which is one of the most important documents in VirtualLab Fusion. So this is typically some result which will be given by some simulations, which we will do later. And now here in the view ribbon, for example, you can change here now the polarization of the electromagnetic field. So you can switch it, for example, from EX to EY. So you see there is no EY polarization because we have used the linear polarized light in the X direction. But of course, there's also an EZ component for a Gaussian beam. And we can also switch now, instead from the amplitude, we can go now, for example, to the phase. And then we see here spherical phase. So that means that our Gaussian beam is not directly in the waist, but is around 100 millimeter away from the waist. And you can also display here the amplitude squared, which is proportional to the intensity. A lot of information we find also in the property browser. Here you see, for example, if you click here on data, you see here that we have here also this Jones vector describing our polarization of our beam. So we saw that it is an linear polarized beam in the x direction, and we see here the wavelength is 532 nanometer, and we also see here, for example, in the sampling parameter. So we see that our computational domain in x and y direction is around 2 millimeter, and we have a sampling distance of 11 times 11 microns. We can also now change here in the ribbons. We can change here, for example, now the color. So we can change it from grayscale to reverse rainbow, which is a logarithmic scaling here of the amplitude value, so that we can see finer details of our field distribution. And we can also click here on interpolate view to make a cubic interpolation to smooth a little bit the view. Also in the view ribbon, you find helpful markers. So for example, you can find here the line marker, and now if you choose that, you can just draw here, for example, a line, and along the cross section along this line is now given here below. So you see here nicely this Gaussian shape. I can also manipulate the position, the start and end of this line here in the property browser. I can go here to view and see here the profile line, and I change here, for example, the starting point of this line and the end point. I can just mark it and press on my keyboard the corresponding numbers, and so I have modified here now, for example, the line, and now it's really parallel to the y-axis, for example. Another important marker we have here is, for example, the point marker. So you can just click here on a certain position, and you see here, for example, on the lateral position, x equals 0, y equals 23 microns, you have an amplitude of the electromagnetic field of 986 milliwatts and a certain phase value. Furthermore, you can use here the view to zoom in and zoom out. In the manipulation ribbons, you find plenty of predefined mathematical functions which allow you to modify or manipulate the harmonic fields. So you can click here, for example, on this button here on the right side to make an Fourier transformation. So now you see the axes are now in the Fourier space kx, ky. You see now a Fourier transformation of a Gaussian, of course, remains a Gaussian. You also have other options. For example, you can manipulate here the sampling, you can interpolate the field to another computational grid, you can manipulate the phase or the amplitude, and so on. So you can always just click there and you have several options what you could do. Also, the detector ribbon is very important. So there you can calculate from this electromagnetic field other physical quantities. For example, you can calculate from the electric field by the Maxwell's equation the magnetic field components, and this you can find over there. Just click the button here, and VirtualLab will show you a new window containing the HX, HY, and HZ field component of this Gaussian beam. So you see that VirtualLab always deals with a fully polarized electromagnetic field consisting of the free magnetic as well as the free electric field components. Another very important feature is the light view. So if you switch here from data view to light view, you see this green color of the Gaussian beam because we have used a 532 nanometer beam, which have this kind of nice green color. So this light view really gives you the visual perception of the human eye. So if you would go into the lab, you would see such kind of Gaussian beam in the lab. And If you really have calibrated your monitor, then you could really display here real colors. And now you could also add now, for example, several different wavelengths to generate some white light. And if you propagate now this white light through some lens system, then you could investigate, for example, chromatic aberrations and could see how this is really influencing also the visual perception. Okay, so this was all about the harmonic field. Let's come to the most important document in VirtualLab, which is the light path diagram. So the light path diagram allows you to specify an optical system in VirtualLab. And there are several options how to open a light path diagram. So first of all, you can click here on the permanent ribbon start. And now you can click here, for example, on new and select here the light path diagram. Alternatively, you see also already VirtualLab offers you here to use a shortcut on your keyboard. Just use Control L to open the light path diagram. So if you open it, you will see always two windows. So the light path diagram always consists of a light path view and the light path editor. So, and these both windows are coupled to each other, so they cannot exist alone. So if you close one of them, automatically the other one will close. And you can always switch between these two windows by clicking here on the right upper corner on this button, and you will always find the corresponding light path view or light path editor. So the light path view now really represents your optical table where you can place several optical components, sources and detectors as you would do it, for example, in the lab. So, for example, we could just simply take here from light sources, from our predefined light sources, we could place here now, for example, by drag and drop, a plane wave source. And furthermore, we could go here to ideal components, apertures and lenses, and add here an ideal lens. After that, we also would need a detector, and in this case, the most important detector is the virtual screen, which calculates in a plane an harmonic field, and it will generate such kind of window in the end, which we have seen a few minutes ago. So I just drag and drop now this virtual screen here into the light path diagram. And now I also have to connect these different components to each other. So that means I have to tell VirtualLab in which sequence the light will pass through the different components. And I can simply do this by clicking here in the document-specific ribbon of the light path. I can click here on complete sequence generation, and if I do so, VirtualLab automatically will draw a connection between the plane wave and the ideal lens. You can also see, in principle, the same setup here in the light path editor. You see I start here from a plane wave, which has an index 0. So you can also see here this internal index here below. And I go through some standard air. So it's just simply some air representing here this connection. I go to the ideal lens, which has an index 1. And now I also would like to connect the virtual screen after this ideal lens. So I can go here to detectors, and here I find my virtual screen, which has index 600. And I can now select here, for example, the index 1, representing here the ideal lens. And now I have here a connection between the detector and the ideal lens. If I now also would add more components, for example, such kind of aperture, I can just add here by drag and drop an aperture. Now there are several options to include also this aperture here in the system. So I could again use this complete sequence generation button. Alternatively, I also just could go here in the light path editor and go here from the ideal lens and choose here as a next index here the index 2, which is the index of the aperture. And now you see I have now a connection between the ideal lens and the aperture. And now I say, okay, I would like to have the virtual screen now behind this aperture, so I can change now here the index of the virtual screen to the aperture. I can also rename optical components. I can just click there on the name and say, and can give them different names like this. And if I now would like to edit the parameters of the different components, I can just double click on this component. So for example, if I would like to edit the plane wave source, I double click here on the plane wave component and the edit dialog will pop up. And now all the parameters which are related to the source can be edited here. So you can, for example, go here to spectral parameters and you can change, for example, the wavelength. You can also load not only a single wavelength, but a triplet of wavelengths. So, for example, if you use here these 3 wavelengths, you would get such kind of white light color. So you always see here in the preview the color which will be generated by this combination of these 3 wavelengths. And of course, you can also give a list of wavelengths, meaning a more complex spectrum. Let's keep it simple. Let's take a single wavelength. And here in basic parameters, for example, you can also specify the truncation of the plane wave. So we always deal with a truncated plane wave, and the truncation now is, for example, an elliptical shape, and it has a diameter of 1.2 times 1.28 millimeters. You can also modify here the polarization. So currently it's linear polarized in the X direction, but you could also change it to circular polarized or elliptical, or define a general Jones matrix as input. In the same way, you can also change now the parameters of the optical components. You can just double click on the optical components and the edit dialog of the component will pop up. Here we have used an ideal lens. Ideal lens or ideal components always mean that we do not simulate the physical structure of the lens or of the component, but we just simulate the physical effect. So the physical effect of a lens is just introducing a spherical face on the incident beam. And that's why we do not define here any geometry, but we just define here a focal length defining the radius of the spherical wave, which is introduced here by this ideal lens. So this ideal components means also that they are always infinite thin, and it's in principle just a transmission function. So let's keep the focal length here of the lens 100 millimeter, and one can click here on OK. The same you can do with the aperture. So we can change, for example, the aperture to be 12.8 millimeter, and then we can click here on OK, and we are done. In the same way, we can edit now also the detector. So we double click here on the virtual screen, and we can change here, for example, in detector function, we can say that we don't want to see, for example, always the amplitude of the electromagnetic field, but we would like to see directly, for example, the squared amplitude, which is proportional to the intensity. And we would like to directly see it not in grayscale color, but we would like to see it in reverse rainbow. And we would like to have a very fine resolution, so of the final view. So that's why we can increase here the sampling distance, oversampling factor. So that means that the sampling distance will be 7 times higher than the required minimum sampling distance given by the sampling theory. And then we can just click here on OK. And we have almost defined now our first setup. Now we just have also to define our distances between the components, or we have to make a positioning. So we can, for example, say we would like to place here now the virtual screen in the focus of the lens. So that means that we just click here below the virtual screen, and we can specify here now a distance of 100 millimeter in Z direction. And we could also in principle define here an off axis or lateral shift in the X and Y plane. And we can also give here orientation. That means that we could tilt the virtual screen with respect to the optical axis. So you could define here, for example, in spherical angles, a tilt of this screen. But let's keep it simple. We just stay on axis and with a distance of 100 millimeter, and we press here OK. Now you also see here that the distance is given here. So please note that we always use a relative positioning here. That means that this virtual screen is relative positioned with respect to the previous component, which is the aperture here. And if I now would change here, for example, also this distance between the plane wave and the ideal lens, that would mean that then the absolute position between the virtual screen and the coordinate center, which is always the source, would be then the distance between this 100 plus the distance between this relative position between the plane wave and the ideal lens. You can also always find a nice 3D view to see, to check your optical setup. So therefore you can just click here on the View System button here on the right upper corner. If you click here, a 3D view will pop up. So currently what you can see is you see here the plane wave, and in the same plane as the plane wave there is the aperture and the ideal lens, and the ideal lens is infinite thin. So it's not really spectacular. And then you see at the distance of 100 millimeter, you see here now the virtual screen. And if you now have more complex optical setups, you can use the 3D view to check if you have done your positioning in the correct way. If you now also say, okay, I don't want to use this aperture anymore, I want to get rid of this aperture, you have several options. For example, you can add here now, for example, also a stop, and you say, okay, I would like to replace the stop by this aperture. Then you can use here, for example, this exchange element button here in the upper part. And if you do so, then you can choose the index. For example, you would like to insert the stop and you would like to exclude the aperture. And then you just click on OK, on VirtualLab will exclude the aperture and include the stop. You can also mark the aperture, and by delete, you can pressing the delete button on your keyboard, you can delete it. You can also exclude elements. If you click there, then you will get rid of this stop, and you can then remove it also. All the parameters which can be changed in the setup can be also found in the parameter overview. So here, if you click on this button, you have a table, and this table contains all parameters of all optical components, of all light path elements, which can be changed. That means that you could also in principle change here now, for example, the focal length of the lens, or you could change here the position between the virtual screen and the ideal lens. So this is an option to change very fast different parameter, and you can also filter here by different names. So you can say, okay, I'm just interested in the distances, and then this table is filtered, and you will just see the distances which you can vary in the setup. So now we're already ready for our first simulation. So we can go here in the light path editor, and here you can choose now between our three simulation engines. We have this classic field tracing, the geometric field tracing plus, and the ray tracing. And we also have something like called ray tracing system analyzer. So let's start directly with this ray tracing system analyzer. And if we press here the Go button, VirtualLab will generate here such kind of 3D view, and you see here now a ray trace. So we start here with an ideal plane wave. We directly go through an ideal lens, and we focus now the light here onto the virtual screen. I can also generate a dot diagram, clicking here on the 2D view, and then you see that all the rays in this 2D dot diagram are focused really on the central position. So you see that it's really an ideal lens. There are no aberrations, and that's a perfect focusing. In principle, you could generate the same 2D dot diagram if you use here this ray tracing button. Then you just would get the 2D plot and not the 3D plot. But of course, you know that such kind of ideal focusing does not exist. You always have some diffraction effects. And if you would like to also analyze this diffraction effects, you can switch here the simulation engine just to classic field tracing, and without any changes of the setup, now you can really do a wave optical simulation of the setup, and you can nicely see now here such kind of array pattern. So you see here the intensity distribution in the focal plane of a plane wave which is focused by such kind of ideal lens. And if you click here, for example, on the amplitude, you see here now we have this kind of array pattern with this nice rings. And if you use here again this line marker, you see here the cross section along the lines gives you this well-known array pattern. Okay, now in the next step, we can also replace these ideal lines by a more realistic lens. So therefore, we can go here to components, and we can add here, for example, an optical interface sequence. And now we would like to replace this ideal lens by the optical interface sequence. So we can say again, exchange elements and replace number 4 by number 1. And if we do so, we can also delete the ideal lens. And this optical interface sequence now can be really used to specify the real geometry of your lens, meaning that you can specify now the interfaces and the subsequent media. So just double click here on the optical interface sequence. The optical interface sequence edit dialog will pop up. And if you click here now on add, the interface catalog will pop up, where you can find plenty of predefined interfaces. So you find here, for example, some aspherical interfaces or some Axicon interfaces. And you can also go here to templates and find here some, I would say, some standard interfaces like a conical interface, for example. So we just choose the conical interface, we click on OK. Now you see here in this 2D plot this conical interface. Now we could also add the backside of the lens, and in this case it should be a plane interface. And we could again click here on add to add it from the interface catalog, but also the most important interfaces we have specified here as shortcuts, I would say. So we just take here the plane, drag and drop it into this list. So now you have a list of 2 interfaces. You also see here the second interface. And now we can say we would like to have a distance of 4.33 millimeter between the first interface and the second interface. So this is the central thickness you have defined here. And now we would like to replace the material between the first and second interface. It should be not air, but it should be some NBK7. So we can click here on the edit button, and we can click here on the load button, and then the material catalog will pop up. And there you can find plenty of predefined materials, and you can also, for example, find the shot glass catalog with a lot of different glasses Shot is offering. Of course, we have here again this search function, so I can search here for BK, then I directly see that there are just a few of them, and I can choose here BK7, and I see here the absorption and dispersion curves of this glass. And we also have several metals for mirrors, for example, or plastic for plastic optics. And we can click here on OK, and also on OK here, and you see now also the color is changing. So now we really have some glass here in between. And after the interface, again, we would like to have some air. You can also click here on the left lower corner on the 3D view, and we see now the first interface and the second interface. So this already shows you the second plane interface has a rectangular shape, so we don't like to have this. We would like to have a circular shape. So we go here in the plane interface and change here by edit definition size to be elliptic and not rectangular. If you do so, we can click here on OK. We can also change in the conical interface, for example, the radius of curvature. It should be 51.0099 millimeter. And we can click here on OK. If you now watch the 3D plot, you see a plane interface, and the second interface has this kind of spherical shape. Sorry. So in principle, we are now done with the definition of the real lens, and now we could do again the same simulation. I would like to increase a little bit the source diameter so that we get a little bit more aberrations in our system. So I increase the diameter of the source by a factor of 10. And now in the 3D view, you also see that the source plane, which is here given by this green color, is almost in the same size as this lens. And you see the first interface and the plane wave source is directly in front of this interface. And you see here the virtual screen, the distance of 100 millimeter. And if you would now do the ray tracing, we would see that this lens will give us now, first of all, our detector is replaced not exactly in the focus anymore. And you see also the dot diagram here. So that means that at first you have to bring this virtual screen here into the focus, and therefore we have here this focus finder. So you can just click here on find focus and just say go, and VirtualLab now will optimize the position so that the position of the virtual screen is automatically in the focus of this lens. If we now do a ray tracing, we see now our beam is now exactly in the focus. And if we watch the dot diagram, we still see that we have here some aberrations. So not all of the dots are here exactly in the center. And of course, if we do a wave optical simulation, we can also now see that we do not have a nice airy pattern anymore, but we will get some aberrated point spread function. So this is the point spread function or the intensity of the beam in the focus. You can also watch here, for example, the amplitude. And this is not an airy pattern anymore. And interesting to see is also that we have here, for example, now not only an EX polarization, but we also have a very weak EY polarization component. This is due to the fact that we have some polarization crosstalk in our simulation. If we now talk about the simulation of real optical components, we can also use here, for example, the component catalog in VirtualLab. So you can click here on Add from Component Catalog, and then the VirtualLab component catalog will pop up, and there you can find plenty of predefined optical components. So for example, you can go to the aspherical component catalog and you choose some aspherical lens, and then you can just click here on OK, and this asphere will be here included. Now you could replace this asphere by this optical interface sequence. So you could really now use also standard components from the catalog. And another very important feature is that for real components, you always have also the option to change the operation from transmission to reflection. That means that if you change the channel from transmission to reflection, now the light, or VirtualLab would not simulate the light propagating through the lens, but we would simulate, for example, the light reflection, which is reflected at the first lens interface, and then we would place a screen 96 millimeter in front of this first lens, and we would evaluate the light which is reflected back at the front interface of this optical interface sequence. So that means that this optical interface sequence can be also used to specify, for example, some mirrors. But we would like to have it here now in transmission again, and we would like to use another very important feature of VirtualLab, which is the parameter run. So we would like to do some experiment series or simulation series, so that, for example, we would like to vary here in a systematic manner the distance between this lens and the virtual screen, and we would like to vary it, for example, between 96 millimeter and 99 millimeter to make some kind of depth of focus analysis. Before we do this, we will add here another detector. So we can go here to detectors, and we can go here to basic detectors, and then I would like to add here now a beam size detector. So this detector just calculates always the beam size in a certain plane, and I can now connect this beam size detector. And now we would like to vary also by this parameter run the beam size detector, and we would see how the beam size is changing if we move through the focus. So again, at first I show you the ideal case if we are in the focus. So I just position the beam size detector at the same position as the virtual screen. And I can do here the classic field tracing and press go. And now here in the detector results, the beam size will be displayed after a few seconds. And so now you see it here. In X direction, the beam has a diameter of 24 microns, and in Y direction, the same. And now we do the parameter run, and we vary now the distance of the virtual screen and the beam size detector between 96 and 99 millimeters. So we click here on the light path on the parameter run, and this wizard will pop up. And here now you find all the parameters which can be changed in the setup. And I would like to vary now, for example, the distance before the virtual screen and the distance before the beam size detector, and I would like to vary it from 96 millimeter to 99 millimeter, and I would like to do it in 13 steps. So that means that I have a step increment of 250 microns, and I do the same for the other detector. And I can click here now on next, and now you see in the next setup, which will give you now an overview how it will change here the parameters for the different iterations. So you see that they are both changed in parallel. And then we can click here on next. We can choose here now the simulation engine which should be chosen for this parameter run. So let's do it in classic field tracing, and which detector should be used for the evaluation. So I would like to evaluate for each iteration both detectors. I can click here on next, and I can click here now on start, and VirtualLab will calculate now 13 iterations with this different parameter sets. Please note that VirtualLab is highly parallelized. That means that each iteration will be calculated by another CPU of your computer, and dependent on the number of CPUs you have, you can finish several iteration results in parallel. So for example, my computer has 8 processors, and you see already here this 7 or 8 simulation results appeared almost at the same time, because each processor has done his own simulations. And you can also see now we have started here now the simulation, and now a little bit the physical memory requirement has increased. And now after another few seconds, we should have our final result of the parameter run. So you can also see here, for example, always the result of the detector. So at a distance of 97 millimeter of the detector, we have here, for example, a beam diameter of 23 microns in X and Y direction. And we can also make some nice plots when the simulation is finished, which will be done soon. And So the harmonic fields are already calculated, so now he's just doing the last few beam parameters, or evaluating the beam size detector. And now the simulation is done, and now, for example, I can mark all of these results. For example, beam diameter in X direction, I can mark them by just clicking here on this orange part, and I can say, okay, create output from selection, and now I can see how the beam diameter is changing if I change here the distance. And you can clearly see here that the iteration result of 5, we are close, and we have the smallest beam diameter, so that means that we are close to the focus. And we can do the same for the electromagnetic fields. So we can mark all of them. We can switch here to harmonic field set and say create output from selection. And now VirtualLab will generate a container consisting 13 results. Each result represents here one iteration result, and you can now run here through, and you see that the beam diameter is getting smaller and smaller, and then afterwards we are leaving again the area of the focus, and the beam diverging more and more again. So in the end, I would like to also show you very fast an parametric optimization. Let's, for example, assume that we would like to re-optimize this optical interface sequence so that we have here a virtual screen having a focal length of 80 millimeters. So we change the position of the virtual screen to be 80 millimeter. Also, the beam size detector should be now 80 millimeter. So now definitely if you do a ray tracing, you're not in the focus anymore. You see looks like this. And now we can do, for example, here a parametric optimization. So we can click here on parametric optimization. And now again, a wizard will pop up. And here we can choose, for example, now the degrees of freedom. So I would like to have, for example, now I'm allowed to change, for example, the central thickness of the lens. And I'm allowed, for example, to change the radius of curvature of the first conical interface. And I would like to do this optimization by ray tracing. And to calculate my merit function, I will use the beam size detector. If you click on next, again, now you can specify the range, the maximum and minimum range. I'm allowed to vary the radius of curvature. So, for example, it should be allowed to vary the radius of curvature between 30 millimeter and 80 millimeters. And the central thickness should vary between 1 millimeter and 10 millimeter. And the target value, which defines the merit function, is the beam diameter. And this beam diameter should be as small as possible. So we say that we would like to have a target value which should be 0. Of course, I could also define the other constraint types, but in this case, the target value makes sense. So you can now click on next. Now you can choose here between different local and global optimization algorithm. So we will just take here local optimization, a downhill simplex optimization, click on next, and now we can start an optimization. Now we do a ray tracing for optimizing this lens, and you see this ray tracing is pretty fast. So we have already done 45 simulations, and after a few seconds we will end up with an optimized result, an optimized lens. So you see now after 109 iterations, we have VirtualLab has found now a central thickness of around 10 millimeter and a radius of curvature of 45 millimeter. And if you click here now on show LPD, show optimized LPD, you get the optimized setup. And if you now do the ray tracing, you see that we are again here in the focus. And now we could use, for example, a further wave optical simulation. So we could now use this ray tracing optimization result as a starting point for field tracing optimization to further improve the optical system. But of course, this would take a longer time because the physical optics simulation would, each iteration would take a longer simulation time. So more about this combination of ray tracing and field tracing also will be given in the second part of this webinar. In the end, I just would like to show you some small features which help you in your daily work if you work with VirtualLab. So we have so-called calculators. If you use this permanent ribbon start, and you can find here a lot of calculators. So for example, if you work a lot of times with gratings, probably you need from time to time the grating equation. So we also have implemented this as a small calculator. So you can click here on diffraction angle calculator. And here now, this is just a small tool which is calculating always the grating equation and calculates always the diffraction, the direction of the diffraction orders in reflection and transmission. And if you change here now the wavelength of the period, the diffraction orders will change. You can also change here the material behind the grating, for example, or the wavelength. And in the same way, we have, for example, also some Fresnel calculators. So you can calculate, for example, the Fresnel effects with a single interface going from air to fused silica. And then you see here, for example, for normal incidence, you have this kind of around 4% reflection losses. So I hope you have seen that these ribbons give you a fast and intuitive access to all VirtualLab features, and that the light path diagram enables the flexible definition and positioning of sources, components, and detectors. And we also have seen that the parameter and parametric optimization are powerful tools for tolerancing and optimization of optical systems. And in the end, I quickly showed you that we have calculators implemented in VirtualLab Fusion, which simplify your daily work with VirtualLab Fusion.